Hello everybody, it's Mr. Ray here with another math lesson. This time we're going to start off our grade 10 applied math course. Our first unit is called linear relations. So of course we need to understand what that means. So let's start off with some definitions and some terminology so we can speak the correct math language for this. Okay, so in math is all about discovering relationships between two different things that you can measure, and then come up with a model that you can use, like a mathematical model. Once you have that mathematical model and you know it works, you can actually use it to make predictions. And that's really the whole goal of math, is to discover these relationships between two different things and come up with how they're related and how we could predict one value given the other. Okay, so so a relation is just it's basically a description of how two variables are connected. Okay, so they have to be connected. Something like the number of hours you study for your math test and the mark you get on the math test. Those seem to be two different variables or two different pieces of information that would be related to each other. But if I was to look at, say, the temperature in Hawaii and your math mark, well, those two things are not related. So a relation is when the two things we're looking at have a connection and that we could discover the relationship between them. Okay. Now, anytime you have a relation, I've already mentioned, you have two different variables. Most of the time, one of the variables depends on the value of the other variable. Okay, so we call that variable the dependent variable. It depends on the other variable. Okay, and the other variable doesn't depend. It's independent. It could be by itself if it wanted to be. It's kind of like an adult and a baby. A baby depends on its parents, whereas the parents don't really depend on the baby. Okay, so now we're going to look at ways of determining, well, which is the independent, which is the dependent. Sometimes it's a little bit tricky, but hopefully we'll do some practice on that, and you'll discover that it makes sense that yes, that one definitely is dependent on the other. Okay, and then those things apply to all relations in math. Now there's all sorts of different relations. The most common, or the one we're going to start with, is called linear. Okay, so linear, if we were to graph the values of the two variables, we would discover that, hey, look, all those points that we're graphing form a straight line. Okay, and the whole word linear comes from line. First four letters of linear are line, so that's a good way to connect the fact that the graph is a line for any linear relation. Okay, now there's other types of relations that you'll be working with. We're going to take a peek at another type called quadratic at the end of the course, and that's things like things that go up in the air and come back down. Okay, so that's obviously not a straight line. If you graphed it, it actually forms something called a parabola. So, and there's lots of other types of relations as well. That's just kind of the tip of the iceberg. So we're going to start with our discovery of relations. We're going to look at linear relations, okay, in this unit. Now, the key concepts. So now that we've got the terminology done, you can actually describe the relation in 4 different ways. Okay, you could have a table of values, and we're going to look at all of these, so don't worry too much if you've forgotten. But it's basically, normally it's the x values and the y values of all the points that you've discovered that for this relation. So it's a table of values. We've already mentioned you can graph them. That's the second method, or the second form of the relation. The third one is probably the most important, is the equation. So we're going to spend a lot of time trying to create the equation of a linear relation based on knowing one of the other forms of data that we've collected. Okay, it could be the graph, could be the table of values. And then the last one is words. So basically a description of what's going on. And we'll be looking at some of those. So we've got these 4 different forms of describing a relation, in this case a linear relation. So your goal for this unit, this is your target, will be if I gave you any one of these 4, either a table of values or a graph or an equation or a word description, you would be able to create the other 3. So that's really the target knowledge for this unit. Okay, so we'll be looking at all sorts of different ways of doing that, how the different forms are related to each other. Okay, so if you were to graph the relation, we've already talked about that. And all of you should be working with the Desmos application. You can type in the equation and you will get the graph. So you can use a graphing application or software to see, well, what does that equation look like if I graphed it? Or you could graph it by hand and hopefully get the same result. And that result will always be a line. Okay, if it's not a line, well, it's either not a linear relation or there's been a problem calculating some of the points. Okay, so the other form, one of the other forms, the table of values. Table of values is just a set of a finite number of points, somewhere between, I'd say, 4 and 8 points that you've discovered are values for this relationship. Now, when we start looking at that, you're going to discover you can always tell if it's a linear relation by looking at the table of values if the y values are always going up or down by the same amount. Okay, so we'll look at that. And the graph, you can tell if it's a linear relation because it's a line. That's pretty obvious. The third non-word form will be the equation. Now the equation, like I said, it's the most powerful tool. It's the most powerful form of the relation. And the reason for that is you can always get exact values. You can make predictions of that relation for pretty much any value you want and very quickly. Whereas if you were looking at a table of values or a graph, you either have to make an estimate or you might have to redraw the graph or extend the table of values. Either way, it's going to be a lot of work to get all the possible values. Whereas the equation, you just plug in a number and you get the resulting value, the y value, very quickly. That's why the equation is so powerful. It's accurate and it's fast, whereas the other ones are not. Okay. Now, so let's start off with a little exercise. We're going to talk about, I'm going to give you two types of variables, meaning I'm going to describe 2 things that are changing but are related to each other in some way. Not necessarily linear, but possibly. So for each of the following pairs of variables, identify which is the independent variable and which is the dependent variable. And the thing that I find works the best is to, in between the 2 descriptions, put the phrase depends on. So read it out loud to yourself. See if it makes sense logically, what you just said, and then change the order around. So change the order of the variables, still put the depends on in between, and usually one of the 2 orders makes a lot more sense than the other. So when you see that something depends on something else, well, the first thing that depends on, that the first variable will be dependent and the second one will be independent. Okay, so let's see how that works. So we've got the cost of a steak and the weight of a steak. So you can tell that those are related, that if one changes, the other one will change too. So which one is independent, which is dependent? So I'm going to put the phrase depends on in between them and read it out loud. The cost of a steak depends on the weight of the steak. That seems to make sense. Okay, if I change it around, the order, the weight of a steak depends on the cost of a steak. Well, that sort of makes sense, but the other one, the first order, made much more sense. So we're going to say the cost of a steak depends on the weight of the steak. Okay, so that tells us, since the cost of a steak depends on the other one, that means it's dependent. So that's going to be our dependent variable, and by default, the weight of the steak is independent. Okay, so hopefully that exercise makes sense. We'll just keep on going. The next one, we have the number of shirts purchased and the total cost of the purchase. So again, I'm gonna insert depends on in between and read it out loud. The number of shirts purchased depends on the total cost of the purchase. Well, sort of makes sense, but I'm not completely sold. If I change the order around, the total cost of the purchase depends on the number of shirts purchased. That makes sense, that this depends on this. So that, in this case, total cost of the purchase is the dependent variable, and by default, number of shirts purchased is independent. So that basically says, as you change the number of shirts purchased, you'll calculate the cost, which will be the dependent, because the cost depends on how many shirts you bought. Okay, let's go back to math for a second. Your mark on your math test and hours studying for the math test. So again, I'll insert depends on in between and read it out loud. The mark on the math test depends on the hours studying for the math test. That makes sense. Okay, so let's read it the other way just to make sure that was the correct one. The hours studying for a math test depends on your math, sorry, it depends on the mark on the math test. That does not make sense. Okay, it's the other way around. The mark depends on the hours you studied. So mark is dependent on the hours studied. Okay, and I think this is the last one. I'll just double check. Yep. The number of clothing items worn and the outside temperature. So you're thinking, well, that doesn't really seem to be related. And then you start thinking, well, if it gets really hot outside, you'll probably wear less clothing. Or if it gets really cold, you'll wear more clothing to keep warm. Okay, so that's the idea of this one. So let's read the two things together with depends on. The number of clothing items worn depends on the outside temperature. That makes sense. If I read it the other way around, the outside temperature depends on the number of clothing items worn. That just doesn't seem right. Okay, so therefore the number of clothing items depends on the temperature. So number of clothing items is dependent on the outside temperature, which is independent. Okay, so why is it so important that we differentiate between the two things? Okay, so well, if we look at the three math forms of a relation, we've got the graph, we've got the table of values, we've got the equation. So if I looked at, say, the table of values, I'm not going to really do much with it. We almost always, we could use any variable we want for these things, but usually a lot of times we'll put X and Y. Okay, now in this case, X is dependent. It's going to be your dependent value, variable values, and Y will be the independent. Sorry, it's the other way around. I'll just X is independent and Y is dependent. So you pick some X values and then you're going to figure out what's the dependent variable going to be worth. So that's figuring out which is independent and dependent is important when you make your table values. You want to get the data in the right columns, okay? if we looked at the graph, okay, in the graph, you always put your independent variable on the bottom, on the horizontal axis. So again, if we're using x like we did here, that would be x, and the vertical value would be our dependent variable, which is in this case the y. So we've got y, we've got x, okay? And then for the equation, again, we're going to look at this in much more detail, but we always have an equal sign in equation. So it's going to start off with y equals and then something to do with x. Okay, so we're going to have some numbers over here and some other terms. Y will always be by itself. Okay, and again, that's your that's your dependent variable, and your independent variable will be over here on the right side. So it is important, especially if you've got a word description of what's going on, that you can look at the two things and say which one's independent, which one's dependent, and once you know that, you can set up your table of values and your graph and your equation with the things, the variables in the right place. Okay. All right, so now that we've determined what the difference is between dependent and independent variables, what we're going to do now is look at a variety of equations and determine which ones are linear and which ones aren't. So it's either a yes or a no to being linear. If it's not linear, we're not going to try to figure out what kind it is. This isn't the right time for that. We're just going to determine, is it linear or not? So there's a couple of guidelines to determine that. Linear equations always have two variable terms. Okay, so when I say term, a term is could be a number multiplying with a variable. It could be just be a constant by itself. But we're going to have two different terms. For example, if we're using x and y, you'll have a term with an x and a term with a y. You can't have any exponents on those variables, so it's just x and y. Can't be x squared or y cubed. Okay, otherwise it's not linear. And it can also have a constant term. It doesn't have to have, but most of the time it does. So based on that kind of set of guidelines, two variables, each in its own term, no exponents, and possibly a constant term as well. We're going to decide if these are linear or not. Okay, so we got y equals 2x plus 1. Okay, these are all definitely equations. We don't have to look at whether they're equations or not. It's got an equal sign in the middle. That's how we know. So we've got a y term, we've got an x term, we have a constant term. So based on our criteria, that's definitely linear because it's got two variable terms and a constant term. Oops, finish that off. Okay, this next one, x plus y equals 4. So again, you're looking, do I have two variables, x, y? Yes, I do. And it can only be two. It can't be 1 or 3. It's got to be exactly 2. So that's okay. No exponents on either one of the variables. And I do have a constant term. So even though the order is different than the above, it's still linear. Because there's no restriction about, well, the y has to be over here and the x has to be over there. It doesn't matter. It's still linear. So for the same reasons as the first example, that's also linear. This one here, so we had x's and y's, and that's by far the most common combination of variables, x and y. Here we've got an a and a b term. That's okay. It can be any two different letters in different terms. And we have a -6, which is a constant term. So again, we've got two variable terms with different variables in each. and a constant term. So again, for the same reasons, that is also linear. All right, this one here, again, we've got two variables, a and b, but the problem here is they have to be in different terms. They can't be multiplying with each other. So right now the AB, that's one term. Well, that's a no-no, because the A and the B have to be in their own terms, distinct from each other. So because of that, that is not linear. Okay, and that's because the variables are in the same term. So we can't have that. All right, this one here should be a little more obvious. We've got x squared plus y squared equals 16. Okay, and you can see we've got an x term, a y term, a constant term. Problem is we've got exponents. X squared, y squared. So as soon as you, and it doesn't even have to be both being squared. If you see any exponents at all, even on just one of the terms, that's not a linear relation or a linear equation. So the reason for this is the exponents. Exponents of 2 are not allowed. Actually, 2 or more, not allowed. Okay, and the last one here, we've got j plus k plus l equals 35. So it looks pretty good, except for the fact that we've got 3 variables and linear equations can only have 2. So this is also not linear because we have 3 variables, j, k, and l. Okay, so hopefully you can see, you can look at an equation and fairly quickly tell me if it's linear or not. Okay, so that's another skill, obviously. So we've picked up 2 skills so far, determining which of the 2 variables are independent and dependent, and now we can look in the equation and say if it's linear. So now what we're going to do in this example here is I'm going to give you a random, well, not so random, a table of values. I got 3 different tables, and we're going to determine, is this a linear relation or not? Okay, so how do we know that? So let's read the question. The table of values for a linear relation will always have the dependent variable, so that's the right column, going up or down by the same constant number. So it's got to be very repetitive. It's got to be a pattern that you see. It's adding, could be adding 10, could be subtracting 3. As long as it's consistently doing the same thing, that will tell you that it's a linear relation that's being described. Now, the other thing you do have to check is the x column, or the independent column, has to be going up by 1 each time. Okay, so this has to be going up by 1. This has to be going up or down by the same amount each time. If that's true, then this is a linear relation. So what we're going to do, first check the x column. Yes, going up by 1s. You notice I didn't say anything about it has to start at a certain value. It could have started at -20. It could have started at 17. As long as it's going up by 1, we're good. Okay, and then for the y column, for the dependent column, what we're going to do is I'm going to compare the change between each sequential pair of y values. Okay, so we started at 0, we went to 2.5. So if I want to mathematically find what's the change, I take the lower number and subtract the one that was just above it. So 2.5 minus 0, that's positive 2.5. 5 minus 2.5, that's plus 2.5 as well. 7.5. Now, you could also look at this and say, oh, it's going up by 2.5 each time. Sometimes it's not as easy to do it that way. So you have to have a backup method. You know, you could have some decimals here that are a little tricky to work in your head. So you always subtract the previous number from each number. So you can see when I do that, I get plus 2.5 every time. Okay, and when we compare it, we're looking, is that the same value? And for this case, it is. So we can therefore conclude that this is a linear relation, because the constant increase of 2.5. We know it's an increase because it's a positive change. It's going up as we go down the column. So constant increase of 2.5. Okay, so let's try our second table. So let's check the x values. Do they all go up by 1 each time? Yes, it appears they do. And now we're going to compare the y values like we did before. Okay, so for this one we started at 3, we went to 2. So mathematically you could do it as 2 minus 3, that's negative 1. This one would be 1 minus 2, that's also negative 1. 0 minus 1, negative 1. 1 minus 0, well, that's actually positive 1. And 2 minus 1 is also positive 1. So it's actually, you may have noticed I put plus signs here, and you may have been thinking, why do you have to bother with that? Well, it's exactly for the reason here. You may think, oh, these are all 1s, but they're not all the same sign. These first 3 are going down by 1, the last 2 are going up by 1. So because they're not all the same, basically these were different than the previous ones, this is not linear. And the reason is it's not a constant increase or decrease. Okay, last one here. Okay, so we're going to check the x column, which is independent, if you remember. Okay, going up by 1, up by 1. Okay, we're good there. Now we check the y values, and you could probably see pretty quickly that it's decreasing by 10 every time. And mathematically you would do that 90 minus 100, 80 minus 90, etc. So these are all minus 10s, decreasing by 10. Those are all the same. And because they're all the same, that makes this a linear relation. Because constant decrease of 10. Constant decrease of 10. Okay, so that's how we can look at a table of values and determine whether it's linear. And you might think, well, we could have just put these points on a graph and see if it's a straight line. Yeah, that would work. But, who wants to draw a graph when you can just have a quick little method like this without having to graph? So, now one piece of information here. What we did here, I didn't really call it a process, but this is actually we call this finding the first differences. Okay, so the first differences are basically what's the change in the y values as we go down the table. So these are first differences. All these are first differences. So basically the rule is if the first differences are constant, then the relation is linear. Okay, so now you can look at the equation, tell if it's linear. You can look at table of values and tell me if it's linear. You could also, now I didn't do this because it's not really required. You could look at a graph, and how would you know if it's linear? Well, just like we said earlier, all linear relations are lines. So if you see a graph and it's a nice straight line, a line is by definition straight, but if it's a line, it's a linear relation. If it's anything other than a line, even if it's got like two lines stuck together that aren't a single line, well, that's not going to be linear. So now you can look at a graph, an equation, and a table of values and determine fairly quickly if it's linear or not. Okay. So what we're going to do in the last example is we're going to kind of link the four forms of the linear relation together. So if you remember, those four forms were the words, like a word description or sentences, a table of values, a graph, and an equation. We're going to start with the words, so a description of what's going on, and then we're going to create in order. First, we're going to create a table of values from this. Then from the table of values, we create a graph, and then we're going to create an equation. Now, the next lesson we do, we're going to spend a lot of time in how to create an equation from a table of values or graph. So this part will, don't worry if you're not quite getting how to do it right now. Sorry, down here. So we'll get an equation, but we'll come up with a true method of developing that from either the graph or the table of values. Okay, so let's read what's going on here. Chris runs a window washing service. Every time she gets a new job, every time she goes to a new job, she charges a flat rate of $5 for driving to the house, plus $3 for each window she washes. So what we want to do, part A, create a table of values using the variables W for windows washed, number of windows washed, and C for the total amount charged in dollars. So you can see I've already set it up. So we've got a W over here and a C. Well, how did I know W goes here and C goes here? Because the cost of washing the windows depends on the number of windows washed. So cost depends on number of windows. So cost is dependent. And remember, the dependent always goes in the right column, and the independent goes in the left column. So I've come up with some values here. I started at 0 windows washed, and I worked up to 5. And that doesn't cover all the possibilities, but it will at least show us the pattern, and that's what we're after here. So what if Chris drove to a job and the person said, you know what, it's going to rain tonight. I don't want you to wash any windows. How much do I owe you? Well, Chris is going to say, well, I charge $5 just to get there and for gas. So unfortunately, I still have to charge you $5. Okay, so, and that makes sense because that was an expense for her. So what if she drives to a place and they only have one window to wash? Okay, well, they still get charged the $5 to get for the driving, plus $3 for each window washed. So that would be a total of $3 for the window and $5 for the driving. So that's going to be a total of 8. 5 plus 3. What if they wanted another window washed at the last second? Well, that's another $3 to what was already charged. So that's 8 plus 3. And you can see the pattern already. We started at 5, went to 8, went to 11. What's going on here? Well, these are all going up by 3s, right? Because every time we wash another window, that's another $3. So you can, once you get the pattern started, you can basically say, okay, one more window, that would bring the total to 14, and another window, that's another $3, 17, and another window, that's going to be $20. Okay, so that we got our table already. Now what we're going to do is graph the relation. So this is where, knowing the independent and dependent variables, we knew we had to put independent here, dependent here, and on the graph, if you remember, we put the independent on the horizontal along the bottom. So that's going to be W for windows washed, and this is going to be the cost. So this is the cost in dollars. Okay, and now we got to come up with our scale. So this is always a little tricky at first. So for the windows washed, we only went up to 5. Okay, and I've got I think I've got 20 boxes here. So I'm gonna each window wash will be 2 boxes. So every second box is going to be another window. 5, 6, 7, 8, 9, 10. Now I could have made it a little wider. I could have actually made every window was 4 and it would still fit on. But you like to leave a little bit of room. Maybe you could extend your graph and be able to predict, well, how much would it cost for 9 windows. So you don't want to make your graph too compressed, but at the same time you want to leave a little bit of room. And then the cost, so the highest cost we have here is 20, and we already know that this is 20 boxes, so let's stick with that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we're all ready now. We can take these points, and that's exactly what this table is produced. It's produced a series of points that we can put on the graph. The first point is when W is 0, C is 5. So W, it's still on here, W is 0 here, and when W is 0, the cost is 5. So I have a point there. And then if W is 1, so W is 1 is along here, the cost will be 8, because we got 1, 8. Then we've got 2, 11. And hopefully you're seeing already, you can see the pattern of the graph. It's looking like a nice line. And then 3 would be 14 from here. 4 is 17. And then 5 is 20. So we kind of used up all our graph vertically. But if I squeezed it in a bit farther, it would look pretty compressed. So what we do now is we actually join the dots. I'll use my makeshift ruler. Now, here's an important thing for the graph. So this situation, does this mean that the fact that I only did these 5 points, does that mean the graph ends there? No, because I could extend this. I mean, I've kind of run out of room on my grid, but I mean, she could easily wash 8, 9, 10, 30 windows. So this end of the graph has an arrow because it keeps going. Now, what about this end here? Can she wash fewer than 0 windows? No, that's not possible. So we don't put an arrow there. In fact, we just end the line right where it started at 0. So there's our graph, and you can see the graph is a line, so you can conclude this is linear. You can also conclude that this was linear because it went up by 3 every time. I'll just put that in. So if you're just looking at this all by itself, you'd say, oh, that's linear, and now we get down to the equation. So remember the equation, it always starts off with your dependent variable, which in our case is the cost, C. So we want to come up with an equation that tells us what the cost is based on the number of windows washed, okay? So if you think about what the table of values was doing, we started at 5, that was the lowest value here, and then every window we washed, we multiplied the number of windows by $3 and added that to the $5 for the cost of driving. So based on that information, I could say the cost is going to be $5 and I don't put the dollar signs or the units, and then I'm going to add on plus 3 times the number of windows. So this would be, we call this the variable cost, because this cost depends on the number of windows washed. This is the fixed cost. The $5 never changes. It's always $5 for driving, no matter how many windows you washed. So that's our equation. We will spend a lot more time on the next lesson developing this equation. In fact, we'll have methods to look at the table of values and develop an equation directly, or the graph. So I could give you this graph and you'll be able to come up with that equation. Okay, so why is the equation so important? Like I said before, we can now use this to predict any value we want, and it's going to be 100% accurate. It's not guessing. I can't really, for example, this question saying, using your equation, predict how much Chris would charge to wash a house with 72 windows. If I'm looking at this table of values, it only goes up to 5. So if I wanted to answer that question using the table of values, I basically have a couple more pages worth of rows. I keep adding $3 every time. That's very time consuming. Okay, or if I have the graph, it's pretty hard for me to predict 72 windows. 72 windows is way to the right, and I'm going to have to change my graph around to make it a lot more compressed. It's a lot of work. But if I have this equation, I can now use that. So if the number of windows is 72, that means our variable W, which represents the number of windows, that's going to be equal to 72. So now I'm just going to use this equation, C equals 5 plus 3W, but now I change the W to 72. So, oops, I want to put that all over again. So that's equal to 5 plus 3 times 72. All I did was change the W to 72. It's multiplying with 3, and that's equal to 5 plus 216 is equal to 221. So that's very quick, right? That's why the equation is so powerful. And this is not a guess, or an estimate. This is the exact number. Okay? Whereas sometimes you look at a graph and you're trying to make a little bit of a guess. So we're going to answer this with words. We're going to say, therefore, it will cost $221 to wash 72 windows. Okay, so this is a pretty important question. It shows you all four forms, sorry. The words, table of values, graph, and equation. And you can see how we started with just one of the forms. We're able to create the other 3. That's really the skill I want you to develop in this unit. Okay, so you've got some homework questions at the end of the lesson note. Basically covers the same types of examples we did here. So if you could practice those, and then the next lesson we do, lesson 2, we'll be looking at more about the equation of the linear relation and how you can create it, how you can take information from it, and how you can construct it from the other forms. Okay, so that's it for this lesson. Have yourselves a great day.